The concept of that signed area leads us to the idea of the definite integral. The definite integral of function f on closed interval from a to b is the total signed area of f on a to b. We denote this in a similar fashion that we did the indefinite integral. So we take this integral sign, which looks like a big long S, f of x with respect to x. On the bottom and top, I put the bounds of the interval. This is the definite integral. A and b, these bounds of the interval, are called the bounds of integration. Now we have a shorthand way to write and ask for the signed area for a function f of x on a specific interval. We call this the definite integral. It turns out that if you want to break up the interval into pieces, well, you can actually do that. You can integrate from A to B, and then integrate from B to C. And what you've done is found the integral from A to C. This is what we were doing in the previous problems. We were taking signed area, we were calculating one triangle, calculating another triangle's signed area, and then adding them up. This allows us to take a picture which looks like this and break it up and say, let's find the interval from 0 to 3, integral when you've calculated from 0 to 3, and then the integral when you calculate from 3 to 4. So we look at one triangle first, and then another triangle. You can add them up, and that gives you the total signed area. That's what this statement is really saying, is that it is perfectly okay to calculate the signed area in pieces. Let's take a look at this example. This is example 4. We want to integrate 3x minus 2 from -1 to 3. Notice how I said that. We're going to integrate 3x minus 2 from -1 to 3. That's how we describe what we're doing when we're finding a definite integral. Let's go ahead and do this using what we know about geometry. I've graphed y equals 3x minus 2. You can see that from -1 up to 3, part of our line is going to be above the x-axis, and part of our line is going to be below the x-axis. Let me go ahead and do this only on the interval from -1 to 3. If I only do this on -1 to 3, you can see that the line segment I'm looking at is that. I want to find the signed area. We're going to get one area. Let's go ahead and do this. 0 less than y less than 3x minus 2. X from -1 to 3. There we go. So we see this triangle, and then we can do the other triangle. And there we go. The triangle that's underneath the x-axis, if you zoom real close into this point right here is actually 2/3, 0. 2/3, 0 is where we cross the x-axis. So be careful. We go from -1 to 2/3. Therefore, the base of this triangle is essentially length 1 1/3 or 1 2/3. Excuse me. The height of this triangle goes from the x-axis, which is at 0, down to -5. This other triangle goes from 2/3 to 3. Therefore, the base is 2 1/3. And the height of this triangle, it goes from 0 up to 7. Therefore, the height of the triangle is 7. Let's write that down. So the triangle on the left, remember, had area. Area is always 1/2 base times height of a triangle. In our case, that was 1/2. We said the base was 1 2/3. I'm going to write that as 5/3 instead of 1 2/3. And we said the height was 5. So 1/2 times 5/3 times 5 gives me a 25/6. I'm just going to write it as an improper fraction right now. The other triangle, the one on the right, area again of any triangle is 1/2 base times height. We said its base, if you recall, was 2 1/3. 2 1/3 as an improper fraction is 7/3. So it had base of 7/3. And the height of that triangle, we said, was 7. That means this triangle has an area of 49/6. Again, that's as improper fraction. So the signed area, which remember, we can write as the integration. Let's make sure we have bounds on this. There we go. The integration from -1 to 3 of 3x minus 2 with respect to x. That would have been, well, let's go back and look at the picture. The picture shows that the right triangle was positive signed area and the left triangle was a negative signed area. In this case, the total signed area would have had to have been 49/6 minus 25/6. When you take 49 minus 25, you get 24/6, and 24/6 is just the number 4. So the total signed area there is 4. And we would say the definite integral is equal to 4. That's how we write it. We did that using geometry. We can do a lot of other examples in a very similar way. Let's take a look at another example. In our previous examples, we've used triangles and the fact that the area of a triangle is 1/2 base times height to calculate these definite integral, or the definite integrals, which is the same as calculating the signed area. Let's see how this example works out. We want to take the definite integral of 1/4 x plus 3 with respect to x from -2 to 5. And we want to calculate that definite integral using geometry. I've graphed the portion of the line from -2 to 5 that we have. Again, if you would just extend this, this would be the entire line, but we're only looking at the region from x equals -2 to x equals 5. You'll notice that in this case, our line is above the x-axis the entire time. In fact, if you look at the area, the signed area that we're going to be calculating, the signed area I've shaded here in blue goes from -2 to 5, and we have this shape. Now, this shape is not exactly a triangle. It's kind of like a triangle. Well, it's part of it is a triangle. And that's how we're going to accomplish finding the signed area. Here's what we're going to do. You'll notice that at the base of this line here, we are at height 2.5. So -2, 2.5 is this point here. If I take y equals 2.5, you see that line, that purple line, cuts through my signed area. If I take this line cutting through, I can calculate the area by combining the triangular portion that's above this horizontal line and the rectangular portion that's below the horizontal line. Let's take a look at the triangle first. The triangle goes from -2 all the way to 5. The height of the triangle, well, that goes from 2.5 to this point up here. Now, that point up there is 4.25. So the height goes from 2.5 to 4.25. The base goes from -2 over to 5. The rectangular area goes from -2 to 5 and then up from 0, again 0 as our y value, to 2.5 as our y value. You should know that the area of a rectangle is just width times length. So in this case, the length goes from -2 to 5, so length of 7. The width goes from 0 to 2.5, width of 2.5. Let's write that down. Okay, so I've created this. We're trying to find the definite integral from -2 to 5 of 1/4 x plus 3. We saw that the signed area using geometry can be broken up into a triangle and a rectangle. The triangle had base that went from -2 to 5. So 5 minus -2 was the base, and the height went from 2.5 to 4.25. So the base had a length of 7, and the height of that triangle had been 1.75. When I calculate that, 1/2 times 7 times 1.75 comes out to 6.125. The rectangle had length that went from -2 to 5, and the width of that rectangle was from 0 to 2.5. That's the y value. So the rectangle had length of 7. I'm saying length is left to right on our x-axis, and width of 2.5. I'm saying that's the change in y values. 7 multiplied times 2.5 becomes 17.5. Again, rectangle area is length times width. Triangle area is 1/2 base times height. And this is the picture again. So our case, notice that this entire blue area is above the x-axis. So we are going to add the rectangle and the triangle together to get the total signed area. That means the signed area will be 17.5 plus 6.125. So the signed area is 23.625. And that is exactly what the definite integral is. The definite integral from -2 to 5 of 1/4 x plus 3 with respect to x would be 23.625. That's how you can accomplish this problem. I would like you to push pause on the video and try finding this definite integral using geometry. The integral here is integrating from 1 to 4, 2x minus 1 with respect to x. Go ahead and do that, and on the next video, I will show you how that's done.